All right, everyone. So we're going to continue on with all these AX equal to B lectures. And what I want to do today is actually start playing around with a little bit of MATLAB. You could do this with Python. In either case, it really doesn't matter what language you use. They all have AX equal to B solvers, QR decompositions, SVD decompositions. And what I want to play around with a little bit is starting to figure out how to break AX equal to B. And what we've been talking about over the last week is this idea of conditioning and stability. Now, the good news and the bad news. I spent a whole week talking about conditioning, right? I talked about like, oh, you could break stuff, these algorithms, make sure they're stable and make sure that, you have a good conditioned problem, a well-conditioned problem, as well as a stable algorithm. Well, if you're working with MATLAB or Python, they've worked very hard to put tools in there that are all stable and bulletproof and are well conditioned and stable. So it's actually really hard to break AX equal to B solvers in MATLAB, right? So in some sense, this reflects a shift. When a book like some of these numerical linear algebra books, when they were written, like in the 80s, having well-conditioned algorithms was still, you still had to kind of play around with that because it wasn't just off the shelf and you weren't guaranteed that. But now most of this stuff is bulletproof. So even though we spent a whole week, I'm going to show you that like it's almost doesn't matter because it's so easy. It's hard to break this stuff. And I'm going to demonstrate it for you on various problems. And we'll go ahead and go from there. So I'm going to share screen now. So we're going to see my desktop and we'll start programming on my MATLAB. So share screen. I want to do the whole desktop, my whole desktop. There it is. And there we are. All right. So you even see me over there on the side. I'm going to put this way over to, oh, it won't let me. Okay. All right. So there you go. Hopefully everybody can see my screen. And let's walk through some code that we're going to build here. So we're going to concentrate on AX equal to B. And what I want to do with this little code here, and you could do this in Python as well, is start talking about some of the numerical solvers that are solving AX equal to B. And so here's what we're going to do. And by the way, we're going to play around with this a little bit, but I'm going to start off with a matrix that's going to be 40 by 20. So it's going to be 40 rows, 20 columns, right? So it's kind of what we were talking about actually in the last lecture. We were talking about the conditioning of specifically this least squares problem here, which is an overdetermined system, 40 constraints, 20 unknowns. And the way I'm going to make this is I'm going to make the A be I'm just going to make a random matrix, rand n by n. So it's going to make a random matrix for me. And that's going to be my matrix A I'm going to work with. Okay. And then I'm going to compute B, which is the right-hand side, which is just also random. So I have a random A, a random B, and I'm going to solve AX equal to B. Okay. Now, I'm also going to make another matrix. So in general, if I just do this, in fact, let me do the following. I'm just going to show you this. What I could compute here is the condition number of A. We've talked about the condition number. And if I'm here, this is this piece of code, and I run this section, it's going to produce a condition number, which is the largest singular value over the smallest. Okay, so I run this, and the condition number is right there, 4.2181. Okay, so it's actually fine. The condition, what you're worried about is when that condition number is very large. What I mean by large is like, 10 to the 16, you're in trouble. Okay, but 4 is no problem. In other words, it's well conditioned. So I can easily solve this. And one way to solve it is say my solution is just A backslash B. Another way to solve it is my solution is the pseudo inverse of A times B. These are, by the way, two different solutions. And in fact, let's look at what they look like. So I'll make a figure 1 here, which is I'll basically plot these two solutions on a subplot And what I'm going to do is do a bar graph of x, and then, oh, if I can type right, a bar graph. Oh, I should call that like, let's call this x2. That's the second solution. So here's two different ways to solve ax equal to b. One is the backslash, and you ask the following question: what did the backslash do? Because the pseudo inverse, at least I know, is a least square fit solution. What does the backslash do? Well, let's take a look at what these two solutions look like. So if I run this section, there's my two solutions. Hey, check it out. They look the same. So in the overdetermined case, the backslash is equivalent to the pseudo inverse. Okay? So that's the solution. That's the solution for this random matrix. Hey, by the way, this is not generic. So what I mean by that is if I come back up to this piece of code and instead I make this a 20 by 40, so it's underdetermined. So there's 20 rows, 40 unknowns, so it's highly underdetermined. Now let's control. I can do the same thing here. I could just say build these matrices, hit backslash or pseudo inverse, and what do you get? Now they're different. Okay, so in other words, the bottom one here, where my cursor is, that's a least square solution to the problem. And then you ask the question, what's the top solution? And it turns out what the top solution is actually doing a QR pivoting routine to give you a very different solution type. In fact, that solution is pretty sparse. There's only 20 non-zero values, and there's 20 zero values. Okay, so they have different solution strategies. The reason I bring this up is the backslash is actually very smart. The backslash command is amazing, actually. It's first of all, if you try to break it, it's hard. It's well conditioned, it's stable, it understands if you're going over or under or square. It takes advantages of any kind of structure it can in finding a solution for you. Okay, so just have that in mind. All right, so let's come back to here and say that, okay, all right, so this is what we're going to do. Cut this out here. And by the way, let's go back now. We did an over and under system. And let's go back to the 40, and let's do a 40 by 40. So this is going to be a square matrix. And in fact, I need to modify your homework slightly because the determinant, of course, is only for a square matrix. So that's one of the things I want you to play with in your homework. And I didn't say that, so sorry about that. But I'll modify the homework slightly. So I want to look at the condition number, and I want to look at the determinant of this matrix 40 by 40 that I made randomly, and ask what they look like. So if I run this section, here they are. So this is the condition number, 197. And here's the determinant. That's nowhere close to zero, right? This is huge. So it's great. That means I could solve something, right? When do we get concerned? We get concerned when that determinant gets close to zero, right? That's what we were taught in linear algebra. You know, in fact, you know, what we're taught in linear algebra is if you see that determinant go to zero, you're done. Like, what do? Well, we basically say, I give up, right? But now you're becoming all like linear algebra pros. You don't have to give up. We go solve stuff all the time. It's a no condition problem. And so we have to figure out how to regularize it to get solutions. All right. So there we go. Condition number, determinants. And let's go back to programming. All right. So I have a well-posed problem here. The determinant's nowhere near zero, and the condition number is small. What could possibly go wrong? Here's what's going to go wrong, and this is where I'm going to break it. I'm going to make a new matrix B. So B is going to be equal to A. Okay, I'm just going to copy it. And here's what I'm going to do. The last column of B is going to be equal to the first column of B, essentially. So in other words, I have this matrix, which is well conditioned. I'm going to take that first column and put it as the last column. In other words, two columns of the matrix B are identical. And what you know then is you do not have linear independence. So you're rank deficient. It means that the condition number and the determinant are going to like be very different now. So in fact, let's go ahead now and plot. Let's ask what's the conditioner of B? What's the determinant of A? Okay. So that's, oh, sorry, of B. Because B is this matrix that I'm playing around with. All right, I'm going to run this, and you're going to see what happens. Run. Whoa, there we go. There's my answers. So now, here's the condition number. It's like 10 to the 17th, so it's huge. It went from a value of 4, and by that, me copying over one column, now it's 10 to the 17th. So this is usually your warning sign. All right, what's my determinant? Huh, the determinant is 10 to the 6th. Does that look like close to 0 to you? I mean, remember, it was 10 to the 22, but now it's 10 to the 6th. So if you were just looking at the determinant, you'd say like, oh, look, the determinant's not 0. In fact, it's 10 to the 6th. I shouldn't have any problems. Well, you got problems. So part of the deal is determinant computations actually are very unstable. Don't do them. Don't trust the determinant. Trust the condition number. That's really what you want to look at, okay? You want to look at this number right here, this 10 to the 17th, and evaluate the stability of a problem. The condition number is very high, which means you're kind of getting into the range of having an ill-posed problem here, okay, or ill-conditioned problem. But by the way, let me just keep working on this and say, okay, fine. But check it out. I'm going to go ahead and I'm going to do these here. Check it out. I'm going to go ahead and take this and say, I'm going to plot the matrix A. I'm going to just show you what the good matrix A looks like. And I'm going to look at its condition number. And I'm going to solve it with just the backslash. So just go ahead and hit the backslash and get a solution. Now, I already showed you that this was well conditioned, so I could get a nice answer here. But now I'm going to take this ill-conditioned problem. I'm going to plot the matrix B, which is exactly like A, except for the column that last column is the same as the first. Plot its condition number and check this out. I'm going to do something totally illegal. I'm going to solve it, right? We were taught in linear algebra, like if that, you know, if two columns are identical, you walk away from the problem because you can't solve it. All right. We're going to go solve it anyway. So there we go. I'm going to get solutions and let's just run it. And I'm going to show you some stuff here. Actually, I'm going to run it and here's figure 3. So I programmed this up ahead of time so we could be a little more efficient with time. We might be too efficient, but that's fine. Okay. So once I get these solutions, here's the solution X1. And what X1 is the solution to the well-conditioned problem. X2 is the solution to the ill-conditioned problem. And I'm going to plot them just like I did before with a bar graph. And just say, what does X look like? Okay, that's what figure 3 is going to be. So let's go ahead and run it, and we'll get some figures popping out. All right. So first of all, come on. When my figure's up that high, it's trying to grab the screen share. Okay, so here's figure 1. Figure 1 is just plotting the matrix, which is a 40 by 40, and it's on a color map hot, and you're just seeing the values of the matrix, and there's a color bar on the side so you can see what it looks like. Matrix B is this one here on the left, and matrix B, I'm not sure why it keeps putting down those numbers, doesn't move. Erase them. They're the same. The only difference between these two matrices is this column right here, the last column of B, which is the same as the first column. Okay. And actually in P color, the way it graphs it, the last column typically isn't actually plotted. It does an interpolation for the first n-1 column. So the point is that what you're really seeing here is the same thing. However, the solutions now are quite different. And by the way, is anybody surprised I ran it and didn't like choke on this thing? Why wouldn't it just stop the code? Let's go look in our little dialog box and see what happened. Oh, look, it gave me a warning. It still computed it. I have two identical columns, right? Which in theory says you can't get a solution to that. And it just said, all right, warning, matrix is close to singular. Actually, it's exactly singular, right? I just copied two columns. Well, it's exactly singular to what? To 16 decimal places. So it's close to singular or badly scaled. Results may be inaccurate. Okay, so it's very nice, by the way. That's a very polite way to say, maybe you're doing something dumb, right? Of course, we can't say things like that. We can still say computers are doing something dumb for a little while longer until they really become sentient. Then we have to be nice to them and say, well, maybe you could have done it better. Okay, so here it's being nice to us by saying, you know what, maybe you have something inaccurate. And in fact, the condition, our condition, the relative condition number is, that's what rcond means, 10 to 18th power there. So I think this guy is actually 1 over the condition number because I already computed the condition number, which was right there. Okay. In either case, it gave us a warning, but it still computed the solution, right? So I broke it in a way. Well, let's go look at the solutions. So when you look at the solutions, here's x1 on top. That's this guy here. This is the well-conditioned matrix. That's what the solution looks like. It's just some values of x. Notice that on the y-axis, they go from about -6 to 6. That's the range of the y-axis. So they're like, you know, order 1 values. And then when I take that first column and I copy it over to the last column, so in other words, I have 2 identical columns, here is the solution. The thing I need you to look at is right there. You see that? That says 10 to the 15. So 2 of the values, one of them is like 10 to the 15, one's like -10 to the 15. Okay, so it's this extremely different solution. And of course, you don't want to really trust this. What does it mean? Like one of these values is like massive, like 10 to the 15. The other one's 10 to -15. So you can see it complained, but it still gave me a solution. So here's the question. I made a big deal of conditioning last week, right? And talking about this, like you have to be careful for this. And then there's the bigger uber question, which is, yeah, but in practice, how much do I really have to worry about this, right? I mean, obviously I don't want this to happen because this is bad news to have these solutions that come out. However, I want to start playing around with it and show you how hard it actually is to break this stuff. Okay, so let me kill this and kill these plots. Then we're going to keep moving on. All right, so let me come back to the code. And I've designed a little experiment down here, and this is this loop right here that we're going to be looking at. And in this loop, what we're going to do is we're going to start playing around with this and saying, okay, I have a problem. And my problem is the first and last column are identical, like down to 16 decimal places, right? And that's what created this ill-conditioned problem. So I'm going to come back to this experiment and do a couple things. So first of all, I can come here and say, all right, so I'm going to make some new figures and I'm going to show you what x2 is. And I think x2 is right here, right? So this is the ill-conditioned solution, okay? So I'm going to show you that. And I'll make 2 figures, figure 4 and 5. And so I want to show you this. So in one limit, if they're identical to each other, I have this problem. And I'm going to make some subplots with 5 different things because I'm going to make a loop here. And I'm going to show you what happens in this loop. And I'm also going to make a vector C, which is going to keep track of the condition number of the matrix B. So initially the matrix B is highly ill-conditioned, like 10 to the 16. It's huge. All right. So now what I'm going to do is make a random vector, a size n by 1. In other words, I'm going to, instead of just directly copying over first column to last column, I'm going to copy first column to last column and add just a touch of noise. Just small amount of noise. So first I make a random vector. Here it is. Okay. And my noise level, check it out. It's like tiny. My noise coefficient will be 10 to the minus 14. So it's tiny, tiny, tiny bit of noise. Okay. So I do a copy and I add just a small amount of noise, like 10 to the minus 14th level. Okay. It's really small, right? That's almost at numerical round off. But check out what my loop is going to do. Here's my loop. My loop is going to go 4 times through. And what I'm going to do is just add a little bit more noise each time. So I'm going to make a matrix B2. B2 will be a copy of A, which is well conditioned. But I'm going to do exactly like what I did before. I'm going to take B2 and take its last column. So B2 colon end means go grab the last column and copy in the first column of A. And that's exactly what I did before, except for now, notice what I do. Don't just copy it in, add a little bit of 10 to the minus 14 noise. And I'm going to put coefficient J in front of it. So in other words, I add 10 to the minus 14 noise. Second time through the loop, J is 2, 3, and 4. So add a bit of noise, twice that noise, 3 times the noise, 4 times the noise. I just made that up, just to see, like, is, you know, if I make bigger noise, what happens? And then I say, okay, solution is x3. Just backslash it. So it's almost identical to what I did. The only difference is in that last column, which was identical, I've tickled it a little bit, like tickling it down to 10 to the minus 14 to make a modification. And I'm going to ask the question, you know, what happens then? Remember, when we talked about conditioning, we talked about the fact that small changes or perturbations, do they lead to big changes or not? So I'm going to make small perturbations to this ill-conditioned problem and see what happens. By the way, I'm also going to solve this problem doing a QR, a matrix decomposition, which is the QR. The question I can ask is, how stable is QR? Right? I'm going to solve it with backslash, which, by the way, the backslash in this over, like often what we'll do is it tries to do an LU decomposition. That's at least in the square matrix cases, right? And I'm going to just do a QR decomposition first. So I'm going to take a QR of that B2 matrix. In fact, it's going to be economy B2. So there it is. I'm going to put 0 here, which means if there's only 20 columns, make a QR with only 20 columns. I don't want the full QR decomposition. I want a partial decomposition. So I do the QR, that's it. Like, that, how easy is that? Like, just QR matrix, you get out your answer. Like, it's awesome. And the question is, remember when we talked about QR, we talked about how do you compute QR? Well, we talked about you could do Gram-Schmidt, you could do modified Gram-Schmidt, you could do householder triangularization. And, you know, in class, we wrote a householder triangularization code. And for your homework, you're going to do a modified Gram-Schmidt. So you could come back and do the same little example once you've written your code, right? But we're going to take MATLAB's QR. What does MATLAB do? Okay, and there, why did we talk about doing householder triangularization? Because it's super stable and well conditioned. Like, I'll show you, it's going to be hard to break this. That's the moral of this story. So remember, QR allows you to solve Ax equal to b into 2 pieces. First, you solve for a vector y, which is just this unitary matrix Q times b. And then once you get the y, you solve r rx equals to y. And since r is upper triangular, when you do the backslash, it already knows just to do back substitution. So again, the backslash is very smart. All right, so the point about this is to say, what if I actually explicitly do a matrix factorization, put it all in here, and then my solution is going to be bar plot x4. And I also plot the bar plot x3, which comes from doing the backslash. So what I'm going to do then is run through this loop 4 times, just take the noise, double it, triple it, quadruple it, and ask, how well does this do? Notice how small my noise floor is. And then I'm going to actually, at each time I do this, right, I'm going to compute a condition number. Okay, and the condition number is right here. So every time I go through this loop, I add a little bit of noise, right? So copy the column, add just a tiny bit of noise, compute the condition number of that matrix, and then keep track of that condition number. And then I'm going to plot the log of it. The reason I'm going to plot the log is because we know when there's no noise, the condition number is 10 to the 16. Okay, so I will break this off here. And then this is now going to plot for us these results. So let's go ahead and run it, and we're going to get some more figures. All right, so let's start it from here and ask what kind of things we're getting. Okay, and the reason, by the way, I picked 10 to the minus 14 is, first of all, this is the result here, the top and the bottom. This was figure 3, which is, here's the solution for the well-conditioned XA matrix. Here's the perfectly ill-conditioned matrix B, where I just did a direct copy. Okay? These 2 plots are looking pretty identical. And one of the things I want to show you here is 2 things. So the top plot is the solution where I have added no noise. It's perfectly ill-conditioned. Like, it's the first and last column are exact copies. These 3 are now the solution when I add noise, I double the noise, I triple the noise, I quadruple the noise. And the noise is at 10 to the minus 14. And the thing I want to highlight to you is, just at 10 to the minus 14, look what happens here. So this was at 10 to the 15, and now I'm down to about 30. So right away, I just at 10 to the minus 14, my condition numbers, or my solutions here, right, they dropped like 13 orders of magnitude. Pretty impressive, right? In other words, that little bit of noise did an amazing job of well conditioning it. In fact, the other thing I want to highlight is, you see these solutions here, you can't see them that well. I guess I could zoom in, but it's always hard to zoom in the same amount for each one. But these are almost identical. What it's telling you is that, yeah, the solutions you get now, if you have 10 to the minus 14 noise, or twice that, or 3 times, or 4 times it, it's basically saying we all get the same solution with just slight modifications. So what am I trying to say? I think what I'm trying to say is the following. We do care about conditioning. But notice, if you want to condition a matrix, you could just add tiny bits of noise. And it's done. I added 10 to the minus 14 noise. This thing is now well conditioned. It's pretty remarkable, in my view, how bulletproof these algorithms are. And I think this just shows it to you, right? And by the way, this is the same result. I could just make it bigger, right? So that's kind of nice. Okay, this is the same result using QR. Same thing. No noise is at the top. As soon as I add 10 to the minus 14 noise, look at these well-conditioned solutions. In other words, here's different noise levels. Does the solution change? No. The solution's not really changing with the noise. Okay? So that's really nice. Let's come back and run this again. And I want to, and the reason I originally picked this 10 to the minus 14 is because that's so small. But like, even if you say, okay, I add 10 to the minus 10 noise. By the way, this is the log of the condition number. Notice the big jump there that happens. This is the log of it. So like you really see a huge, if I were to plot not on a log scale, it'd be like 10 to the 16 and everything else is kind of okay condition. In fact, let's go look at C, that matrix C. So here's the matrix, the vector C was condition number. So the first one is like 10 to the 17, and this seems to be 0, but let's go actually look at the second component. It's like 10 to the 11. So even with condition number of 10 to 11, your solutions are fine. You really have to be at 10 to the 16 or 15. Like it's got to be like that high, 10, 16, 17. Otherwise, what this is showing us is you're fine. You get perfectly good answers, and it seems to be perfectly well conditioned. Okay? So that is, I think, an important story here. In fact, let's go up to here, run, pop this again. And again, even more, oh, come on. I want that guy to disappear. Hold on one second here. I don't know if you can see the screen share. The mic comes down and it's trying to tell me to stop share, but I want to keep sharing with you guys. Right, let's kill this. And again, perfectly, what looks like perfectly reasonable, stable solutions to the problem. And again, this is almost still conditioned, right? Like these two vectors, the only difference between the first and second, it's down, like I said, you're making, like if you plotted them by the naked eye, they look identical, but you're now down at this very small level of where you're making changes, right? This is now 10 to minus 6. So here's something important. I'm going to go off screen share for a minute to say something. So here's the moral so far of what we're doing for the numerics. We're going to come back and do one more experiment in a moment. We worry about conditioning. People have worried about conditioning for a long time. The advantage you have being around in 2020 is that we are now at computers really started coming to people like generic people like you and me. Like I could get a computer and a desktop in about the 80s. Before that, it was sort of like they were hard to come by. There were a few people that had computers they could do some computations on. But the 80s, it started being, okay, now we have PCs, generic people can have access to a computer and do computations. And at that point, obviously they were starting to figure out this whole game around conditioning and stability of algorithms. We're now 40 years past that, right? And being 40 years past that is kind of awesome. It means that what they did is they figured a lot of this stuff out. And they said, oh, all right, well, we'll build all of these algorithms that you call, and we'll build them to be stable, robust, well-conditioned. So it's really hard to break these problems. Okay?
Professor, I have a question.
Yes.
So in your for loop, I think you're graphing the logarithm of the answer. And if the logarithm goes to like 30 or something, I think it's too big.
Yeah, I can take no, the logarithm of the condition numbers, it went up to 10 to the 17.
Okay, gotcha.
Yeah, so the log, it went up to 10 to the 17 was sort of like the ill-conditioned one, and it dropped from there. Because if I didn't do the log, you could see one just giant spike and everything would look like it was 0. So that's why I did the log.
Gotcha.
Yeah. And so you have these really stable algorithms available to you to use, and they're well-conditioned, stable. So in many ways, even though I spent time talking about conditioning and stability, in practice, a lot of these things are pretty bulletproof. And if you do see a warning, by the way, you should probably pay attention to it. Because if the warning says, hey, you saw that warning, this looks kind of big. maybe you shouldn't trust the solution. If it's saying that, then it probably means you have two columns that are identically the same, right? And then you do have a problem with ill conditioning. But you notice how it announced itself. It's not like I was going along, I had no idea. This thing said, hey, when I solve that, I'm going to give you a warning about the solution I give you. So this is fantastic, right? So you can have some ability with these methods today that are built to handle modern computing. Now, let's talk about scientific computing in general. So a lot of where AX equal to B is used is in like doing scientific computing problems where you're doing iteratives of these solves. You're solving AX equal to B repeatedly, and your solution from one time step maybe matters for the next time step. And in fact, that's where I tend to use AX equal to B a lot, is solving these time-dependent problems where you have a bunch of AX equal to B solvers so that you can advance your solution forward in time. And then if you have ill conditioning there, you can say, well, I'm concerned because I'm going to keep propagating this error. But let me tell you something interesting, what we just observed. A lot of time-stepping algorithms like OD45, let's say, fourth order Runge-Kutta, the accuracy is 10 to the minus 6. That's numerical round off. So if I were to come in here and say like, well, I can just make it well conditioned by adding 10 to the minus 10, that's still 4 orders of magnitude below the error I'm making in my time stepper. So kind of easy to make this thing pretty stable, right? You say like, if it's really that ill conditioned, just throw some noise on it way below this 10 to the minus 6. It's well conditioned, give me a solution. You saw it's pretty stable according to the way, right? So there's a little bit of, I mean, how do I teach this to you guys? I'm trying to make you responsible citizens of the computing world while at the same time balancing the fact that like, dang, people have worked really hard so that you can concentrate on doing science rather than worrying about whether your code's going to blow up on you. Okay, so that is some Uber commentary around that. All right, I'm going to come back and do one more little example here. So let's go to a screen share again, desktop, share, boom. So the second example I want to do here now is I want to do sort of a comparison. And the only difference in this routine from the previous routine is you see where I generated the noise, the random noise. I now do it in the loop. So I'm going to fix the noise level, but when I go through this loop 4 times, instead of increasing the noise, I'm going to give it a different perturbation every time. And I'm going to ask the question, if I perturb it differently, does it change the solution a lot? Remember, that was kind of the idea. It was like, yeah, but what if I have different noise on here? Would it generate a very different solution? So I'm going to start off with a little bit higher noise, 10 to the minus 6. And I want to run this with the goal of, in fact, I think this is figure 7, sorry, doing the same thing. I have a QR decomposition. I have the backslash, and I'm just going to ask the question. Before, what I did is I took the same noise and just said, what if it's bigger? Here, I'm going to do 4 runs with 4 different noise realizations and ask, does the solution change a lot? And I would be very concerned if it did. Okay, so let's run it. Yeah, I'm going to run the whole code now. And this is really starting to get to this point, which is, well, maybe the noise I pick matters. All right, well, here you go. These are the solutions. In fact, let me just concentrate on one of these. The QR and the backslash give you the same thing, but I'm just going to concentrate on this picture here. And what I want you to concentrate on is the top one of this column is the perfectly ill conditioned. This is like two of those columns are exactly the same. But what you're seeing from 2, 3, and 4 down, you do see some variability, right? Look at this. It's a little bit different. Every noise configuration is a little bit different. But I'm going to start saying, yeah, okay, but I'm perturbing at 10 to the minus 6, right? So let's actually perturb it down here where I just touch it a little bit with perturbations, because 10 to the minus 6 is already starting to be a little bit bigger. Oh, am I not screen sharing? Sorry, I thought I pressed run. Let me go back to here. All right, I'm going to make it 10 to the minus 10, and I'm going to run this thing. And you're going to see that basically I'm going to start, oh, actually 7 and 8. Okay. So each one is going to give you a little something different, actually. So this is kind of interesting, right? So actually, when I ran this before, I actually didn't quite see this. so that, this is news to me. Okay, 10 to the minus 10, you start to see that you get some variability in these 4 different solutions. Okay, let's make it even smaller. Okay, let's go down. Okay, so let's see where this limit is. I was playing with this earlier, and I swear they all look the same. All right, let's do it again. I love it when my code does something different in live demo than what I was actually playing around with. All right, here we go. All right, different noise configurations, and then you start to get different configurations here. Notice that you still get these big spikes here. Those are the dominant parts of the solution. And then it wiggles these guys in the middle differently for each different noise realization. Okay. So, but you know, all of these solutions, so that's concerning, obviously, right? Because now we're talking about this conditioning. As soon as you back out of that 10 to the minus, as soon as you start adding a little bit of noise here, right, you can sort of regularize this. And in fact, if you wanted to regularize it so you get good solutions, you might even drop this further just to say, I just want to add something like this, which before I had no problem with. And then I can run this thing and see what the solutions look like. And then, yeah, okay, so then it is starting to give me a problem. Oh, that's interesting. I swear, you guys, I ran this before and they all look the same. Maybe I was not plotting things correctly. You still get the big spikes. That's what dominates. But yeah, these guys are all a little different in the middle for both QR as well as the backslash. And in fact, I think the backslash is just doing a QR to solve this for the underdetermined. So this is sort of a good little code to play around with. And so I'm going to send this to you guys, and you get to play around with it. And you can start seeing a little bit of some of the kind of ideas that we have to start thinking about in this linear algebra framework, right? Which is, I want to start thinking about, what do perturbations do to my solution? What does it mean to be ill-conditioned? And again, being perfectly ill-conditioned, and soon as you walk off that perfectly ill-conditioned, your condition number drops sharply. And in those cases I was showing you, there is no warning about, hey, you know, maybe you shouldn't trust the solution. You get a perfectly valid solution and it's not going to complain. In fact, I think you have to have a condition number of over 10 to the 14th before it warns you of something. Okay. And so these are kind of good examples to start thinking about. It's just AX equal to B. And in fact, the rest of this week, we're going to talk a little bit more about AX equal to B in general and solution techniques for it. Because if you remember the first day of class, I showed you all these matrix decomposition tools that generate solutions for AX equal to B. We want to talk about which ones are cheap, which ones are expensive, which ones are stable, which ones are unstable. These are all things that matter quite a bit when you go to compute solutions, especially for square matrices, overdetermined, underdetermined, right? So you want to start thinking about, what are some strategies to pick solutions for yourself as you go solving these things. And it's 3:14. It's pi. So we're going to stop there and take questions.